Hello, and welcome to Backer Breaks It Down. In this episode, we are going to look at tangents to a circle, focusing on the tangent theorems in this lesson. So recall that a tangent is a line in the plane of a circle that intersects the circle in exactly one point. And we call this point the point of tangency. So we recently discovered a special relationship between the tangent to a circle and the radius. Okay, and that brings us to our first theorem, the tangent to a circle theorem. So if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So the tangent is perpendicular to the radius, which means where they meet, we're getting a right angle. Our second tangent theorem and relationship that we previously discovered is the two-tangent theorem. And it says if two tangent segments are drawn to a circle from an external point, then those segments are congruent. So over here, AB and AC are tangents. So that means segment AB and segment AC are congruent. So let's take a look at some problems where these theorems are being applied, right? So the first one, take a look at that diagram. Yeah, so notice that like BC is tangent to the circle, and where BC meets the circle at its radius, remember that point of tangency is B, but where the tangent meets the radius, it's perpendicular, which means that there's a right angle there. Okay, which means triangle ABC is a right triangle, right? And if you think about other right triangles that we've seen so far in this chapter, yeah, we've always had to use Pythagorean theorem in those problems. So I'm thinking we're going to do the same thing here. So I'm going to take like the leg squared. So one of the legs is the radius, plus the other leg squared. And like this is going to be equal to the hypotenuse squared. Now the hypotenuse in this triangle is the combination of the segment with a measure of r and the segment with a measure of 8. So we're going to call it r plus 8. Okay, so that's like the whole hypotenuse. So the hypotenuse squared. Now I will need to like expand r plus 8 quantity squared, and so I can FOIL it out, or I can make a table of products, but I am going to have to expand r plus 8 quantity squared. So I'm going to go ahead and do this, right? Wow, I know I was really fast, huh? So let me get out my highlighter. So r plus 8 quantity squared becomes r squared plus 16r plus 64. And so notice I have an r squared on both sides of my equation. So when I go to get it equal to 0 to like solve the quadratic equation, well, guess what? It's not a quadratic equation at all. The r squares canceled out, so I'm basically solving a simple linear equation, and I get that r is equal to 12 feet. So that was the example of the tangent to a radius to a tangent, you know what I mean, that they're perpendicular. So now for our two-tangent theorem. Tangent segments from the same point outside the circle are congruent. That's what the two-tangent theorem says. And so in this problem, AB and AD are tangent to circle C. So what I know then is that like they're congruent, because if they're both tangent to the circle from the same external point, that's going to make them congruent. So I can create an equation where I'm showing that their measures are equal to each other. So I'll have like 3x squared plus 2x, my goodness, really, minus 7 equals 2x plus 5. It's really, really sorry that my computer's like glitching out on me. So that's our equation. And then since it's a quadratic equation, we do need to get it equal to 0 before we can go about like factoring or even using the quadratic formula to solve it. So I've already done all of that. So let's take a look. So we started with our initial equation, right? And then I got it equal to 0. And so I just brought over the 2x and the 5. So I have a nice simple quadratic that I can solve by factoring. So take out the common factor, write down what remains. So what remains is x squared minus 4. That's a difference of 2 squares, so I can factor that a little bit further. And so I end up algebraically with 2 solutions that x is positive or negative 2. And both answers work here, because if x is positive 2, then our tangents are each 9 units long. And if x is negative 2, then our tangents are each only 1 unit long. So both answers work. Another place where we can see the two tangent theorem are in problems like what you're seeing here. Okay. We've got circumscribed polygons. So what that means is there's a polygon that's tangent to the circle, like all the sides of the polygon touch the circle in one place. You see that? So remember, the two tangent theorem says that tangents drawn from the same external point are congruent. So like in number 3, that means like these two segments would both be congruent. The same with these two. And then of course the same with the last 2 sets. Okay, because tangents drawn from the same external point are congruent. I want to find the perimeter of the triangle in number 3. So now I can apply, that whole congruent thing. So both green segments, I should say, are 10.5. Both blue segments are 11.2. I can figure out the purple segment length because like the whole side is 23.2. So if I subtract 11.2, that's going to give me, I believe it's 12. So now I know the length of basically all 3 sides. And so all I have to do is, well, add them all up. So let's do that. So I ended up with a perimeter of 67.4 units after I added up all my sides. Okay. 4 is a little bit different. It's called like a walk around problem because we are like going to take a walk around this polygon here. So I'm just going to go and I'm going to highlight all my congruent tangents. Okay, just because I think that's going to help us be a little organized here. There we go. Beautiful, right? Okay. So in this problem, they tell us that AB is 10, right? So AB is 10. That BC is 15. And that AD is 18. Right? And they want us to find CD. So you can probably see how it is a little bit different than what we just encountered in the previous problem, because they don't give me any of the individual segments. They're only giving me a side. So what I can do is I can call like any one of my little segments, I could call it X. So maybe I'll call this one X, right? Which means the other yellow segment is also X, okay? If we look at segment AD is a total of 18 units long. I know that part of it is X units long. So what that means is I can represent the green segment by taking the whole side of 18 and subtracting the little bit that I know is X units long, right? And so I kind of want to use this idea of the whole side minus what I know, and I want to walk around this problem. So I'm going to continue doing that, okay? So that means segment EB would be the whole side, which is 10, minus what we know, which is X. Both purple segments are going to be that. when it comes to my blue segments, the whole side is 15, right? So for my two blue segments, the whole side is 15, and then I have to subtract the part I know, and I know that part of it is 10 minus 5. And those are both blue segments, right? So now if you look, side CD has a segment that's 15 minus the quantity 10 minus x, and another segment that's 18 minus x. So I know that's kind of weird looking, but whatevs, it is what it is. But CD is the combination of those two segments. So 15 minus 10 minus x plus 18 minus x. So basically, I'm just going to like clean this up, combine like terms, and what remains will be the length of CD. So be careful when you're subtracting that quantity. Make sure you subtract both parts. So I'm going to minus the 10, and I'm also going to minus the like minus x, so that will become plus x. And so notice what's going to happen to the x's in this problem, right? Because you've got a positive x and a negative x, so those two x's are going to like cancel each other out. So I've got, the 15 minus 10, which is 5, plus 18, so I'm looking at 23, and that's the length of CD. So yeah, but they call that a walk-around problem. But ultimately, we found the length of CD using our two-tangent theorem. So you got the two-tangent theorem that says tangent segments from the same drawn from the same external point are congruent, and then of course the tangent is perpendicular to the radius, and that's how Bakker breaks it down.